Hello and welcome. These are the solutions to quiz 23. So which change below leads to a release of energy? Separating two cations from each other. So you have two cations that somehow were brought together. They would be unhappy. If I could release these two cations, they would release energy. If I could separate the cations, I could get a release of energy through their release. So that should release energy. Breaking a chemical bond requires the absorption of energy. So if I have a bond, like imagine I have H2 going to two hydrogens, this is always going to require energy to be absorbed. Why? Well, there's something that holds hydrogen together. You have to break that attraction if you want to separate the two H atoms. So there's something that allows the two atoms to bond together. It's the sharing of electrons through the covalent bonding. You can imagine the same thing's true of like sodium chloride. It's not sodium. If I have sodium chloride, Na plus, Cl minus, if you have a plus and a minus cation that are electrostatically attracted together and you want to separate these, you have to have energy absorbed in to separate the ions. You have to break the attraction. Well, there's no attraction between the two positive forces. There's actually repulsion. So you get that repulsive energy back when you separate the cations. So we don't get that energy. We have to absorb energy for two bonds to break. If we want to bring two anions together, that has to be accomplished by those anions absorbing energy. So bring two anions together, they repel. So the relative energies, you make those anions closer, his energy goes up. So bring the anions together, the energy is going up. None of the above is not the right answer. So the right answer here is separating the cations. So as the salt dissolves in water, the solution temperature drops. What is the sign of Q reaction and Q surroundings? Okay, so the key is the solution is the surroundings. And so if the temperature of the surroundings drops, the heat of the surroundings drops. This Q is just MCS delta T. So if this is dropping, delta T is dropping. So the temperature is dropping. Okay, and now Q reaction, negative Q surroundings. So if the reaction temperature is dropping, it's because the reaction is absorbing heat. So the surroundings temperature is going down because it's losing heat. Where is it going? It's going to the reaction as it absorbs heat. So Q reaction should be positive. Q surroundings should be negative. A blank delta H corresponds to a blank process. So a negative delta H would correspond to a exothermic process. A positive delta H would correspond to an endothermic process. A zero delta H. So if delta H is zero, it would be no change in energy. It would be, I don't think we gave this word. I wouldn't expect you to pick this word out of the list, but isothermic would be the word there for the reactants and products having the exact same energy, would be isothermic. So iso, just the prefix for same. I don't know if I'd expect you to recognize that or not, but the key is that B is the right answer. 4, which of the following is an endothermic process? So endothermic requires the absorption of energy. So ice melting, ice in the freezer is cold, stays frozen until we warm it up, until we give it heat. So that means it's endothermic. Water freezing is the opposite of ice melting. Water freezing, we have to take heat away, we have to cool, take the heat away from the warmer liquid water. Boiling water is endothermic. Water has to absorb energy in order to boil. When HCl and barium hydroxide are mixed together, the temperature of the solution increases. That means it's exothermic. It means the reaction is releasing heat. That's why the temperature is going up. So that would not be one of the answers. The endothermic reactions, A and C. Which of the following statements is true? Delta H is an intensive mass-independent property. This is false. Delta H of a reaction, like A goes to B. Let's say delta H is like 10 kJs. If you have 2A goes to 2B, delta H is now 20 kJs. So we've doubled the magnitudes. Delta H is independent of the states of the products. That is untrue. Delta H depends on the physical states of the reactants and products. The enthalpy of a reaction, say where water in a combustion reaction is produced as a liquid, is different than the enthalpy where water is produced in the gaseous state. So we have state dependent. So it depends on the state of the reactants and products. Delta H is a path independent function. This is true. Now what this means is if you go from imagine going from A to C, let's say has a delta H of, let's say, plus 20 kJs. So A directly to C, delta H is plus 20. If we have some other reaction where, say, A goes to B, let's say A to B, delta H is equal to plus 10 kJs. Then B to C better have a delta H that's equal to plus 10 kJs as well, because when we add these up and B cancels, A directly to C must be the sum, which would be 20 kJs. So A to C, it doesn't matter how we get there. If we go through B, if we go through 2 intermediates, 3 intermediates, 4 intermediates, no matter how we're using the reaction, delta H is the same. So delta H is a path-independent function like delta E is. Now delta H is exactly Q reaction in a closed system. This is when you have a closed system. Delta H is only approximately equal to the heat change at constant volume. Delta H is exactly equal to the heat change, though, at constant pressure for the open system. So this statement would be true if this were an open system, but not for the closed system. So as written, that statement is not true. Delta H for the forward reaction is the reciprocal of the delta H for the reverse reaction. The reciprocal is 1 over, and that's not true. If you flip a reaction C to A, delta H, you flip the sign. So it's a negative of the sign, not the reciprocal. To answer the question would be the state function one, C. Q and W are the big things that are not state functions. Like Q and W depend on how you're using the reaction. Like, let's say you're combusting a hydrocarbon in a car. The car is moving on the street, so the sign of W is negative for the reaction. You're heating up the engine block. Sign of Q is negative. The delta E for the process and the delta H for the process is also going to be giving off heat. Delta E is negative as well. That these are the state functions. These just depend on how much the reaction actually has taken place, and they're locked in. These can be anything. Like the sum of the heat and the work can be, it depends on how we're carrying the reaction out. If we're, how we're physically, like allowing the mechanical system to operate. We could get more work, move the car more, less heat. We can get more heat if we put the car in neutral and just rev the car up. So these are depending on how we're using. So these are path dependent, is the idea here. And then these guys are path independent. So these are kind of the, how far away two lines are on a map. The Q and W are kind of like, how do you get there? Like you can take a lot of detours that require you to travel a greater distance. So Q and W are kind of like the idea of like the total distance traveled on a trip, whereas the distance between 2 points is always a constant. That's what delta H and delta E are kind of like. All right, number 6. What volume in milliliters of HBr will completely react with 1.55 grams of zinc, according to this reaction here? So let's start with what we're looking for. Number of milliliters of HBr be equal to 0.155 grams of zinc. I gotta go to moles. So zinc is 65.38 grams per mole. According to the reaction, for every 1 mole of zinc that reacts, we need there to be 2 moles of HBr present. And then we're adding HBr, where it's 0.265 moles per liter. And 1 liter, 1,000 milliliters. Sometimes I just write this step here, where I just go, instead of writing here, I just say, well, 1 liter is 1,000 milliliters. Kind of shorten the steps. Now you can write it as 2 steps. I don't care what you do. But that's why sometimes I write it out in a little bit more shorthand form. 0.155 divided by 65.38 times 2 divided by 0.265. Writing this out meticulously as moles of HBr per liter of solution is really helpful in a problem like this one. Helps us make sure we're dividing by 0.265 versus perhaps multiplying by it. Okay, so I get 17.9 milliliters of the HBr solution would be required to completely react with 0.155 grams of zinc. Number 7, got a sample of limestone, mineral containing calcium carbonate dissolved in 25 mils of acid, which allows this reaction to take place here, where calcium carbonate reacts with acid to produce some products. To examine the amount of HCl that remains after this reaction is completed, the mixture is titrated with base. So we're adding HCl here to react with all the calcium carbonate in our sample. Now this sample here is not 100% limestone, or like it's 100% limestone, but limestone is not 100% calcium carbonate. There's other things in it too. So we don't know how many grams of that sample is just due to the calcium carbonate. Now presumably HCl only reacts with the calcium carbonate, no other part of the sample. And so we add an excess of HCl. How do I know I'm adding an excess? Well, the remaining solution is titrated with base, and it takes 13.2 milliliters of the base to completely react with it. So I'm titrating the excess HCl plus sodium hydroxide to go to sodium chloride plus water. And so the excess HCl, I can figure out how much of this is in excess. Let's go moles here. It doesn't tell us what to do, but the number of moles of excess HCl, I can figure this out by taking the 0.180 moles per liter of solution of the sodium hydroxide solution, multiplying by the volume that was used, and that's moles of sodium hydroxide now, and for every 1 mole of sodium hydroxide we had to add was due to the presence of 1 mole of excess HCl. And so what that means is I have 0.180 times 0.01322 moles, 0.00238 moles of HCl present in excess. Okay, now from the amount that's in excess, how much did we initially add? We initially added 0.0250 liters times 0.2 moles per liter HCl. So we initially had added 0.025 times 0.2. So we initially had added 0.00500 moles of HCl. So do you see how we can calculate how many moles of HCl reacted? The number of moles of HCl that had reacted would be the 0.00500 moles that we initially started with, minus the amount that's left over. That's 0.00262. Now from the moles of HCl that had actually reacted with the calcium carbonate, we can figure out how many moles and how many grams of calcium carbonate had to be present. So the number of grams of calcium carbonate that had to be present, I would start with my moles of HCl that reacted. Multiply by every 2 moles of HCl that we had to add, means 1 mole of calcium carbonate was present. And then I need to use the molar mass of calcium carbonate. Nice that they've given it to us, but it's 40.08 grams for calcium plus 12.01 plus 16 times 3, 100.1 grams per mole. So 0.00262 divide by 2 moles of HCl per mole of calcium carbonate times 100.1 means we have 0.131 grams of calcium carbonate in that sample. So it turns out it's mostly calcium carbonate, so the percent of calcium carbonate in the sample will be equal to 0.131 divided by 0.139 times 100%. That's 94.3%. Okay, now if you look at a question like this and you start memorizing how and why you're doing the problem the way you do it, you're missing the point. The point is, this is just a problem that uses the concepts of reactions, molarity, concentration units, and it's just a word problem. It's probably among the hardest problems we could ask on the topic of solution stoichiometry. I would normally, say that you should expect to see a problem that looks just like this again on the exam. This is just like one example of an application problem that was previously on a test. So don't overly stress out about whether or not a question like this could be on your test. Think more about how can you get good at solving problems like this the first time if you happen to have missed this problem. Just think, how can we recognize simple problem-solving ideas within problems, or even if you're still stuck on how it is that we're solving it. I mean, it's just the concept of there being two reactions that take place, and it requires some bit of thought. And if you need to sketch a picture, if you need to, try it a few times in order for this simple problem-solving ideas to shine through in the problem. Let's move on to the next example. So we have a mass of a sample of a diprotic acid that's being dissolved in water. We're adding sodium hydroxide to react with it to reach the end point. What is the molecular weight of the diprotic acid? So the sodium hydroxide, since the acid is diprotic, is going to be reacting with both of the H pluses. So by diprotic just means I have two H pluses. So I'm going to need two sodium hydroxides. So I'm going to produce Na2A to balance out my two sodiums pluses with my A2 minus. I know it's a 2 minus because I have two H pluses here. And then I'm going to have two waters that form. The key is the 2-to-1 ratio of the sodium hydroxide to the H2A. So the molar mass, that's what we're looking for here. What's the molecular weight? It's also the same as the molar mass, or it's the same number as the molar mass. So the molar mass of the sample would be equal to the number of grams of H2A divided by the number of moles of H2A that are present in the sample. So we already know this is 1.2345 grams. The question is how many moles of H2A are there? Well, I get this quantity from the sodium hydroxide. So I'm going to do the math. I'm running out of room, but I can do the 0.04410 times 0.6124 moles per liter to get to get the moles 0.02701 moles of NaOH that had to be added. Now for every 1 mole of NaOH, for every 2 moles of NaOH that we had to add from the balanced reaction, means there's 1 mole of H2A that was present. So I just calculated the moles of H2A that had to be present. So I'm just simply dividing by 2. And I'm going to divide this number into 5 grams. Gives me a molecular weight of 370.3. Oh wait, I'm sorry, I used the wrong mass. I did 5 grams. I used the mass in the previous, some other example. 1.2345 divide by, hold on, let me go back to the problem here. 2. Okay, so I'm taking 1.2345 grams, divide by the number of moles. I get 91.4. Not getting a right answer, so I'm just going back through seeing if I miscalculated something. Oh, I don't know who wrote this problem. I wrote this problem. 1.2345, not 1.2345. 1.3245 divided by that value is 98.1, 98.09 grams per mole. Okay, now the key here is whenever you have a reaction taking place, you should be able to write the reaction of what's going on. So an acid is going to be completely neutralized. So a monoprotic acid takes 1 mole of sodium hydroxide to neutralize it. Diprotic takes 2 moles of sodium hydroxide. A triprotic acid takes 3 moles of sodium hydroxide. For example, if you have H3PO4, this can be completely neutralized with 3 sodium hydroxides to go all the way to Na3PO4 plus 3H2O. So the key here is triprotic. So all these H pluses fall off when we add the sodium hydroxide. Now let's take a look at our last question. So nickel solid can be blanked by lead nitrate, and nickel nitrate can be blanked by lead. So what kind of reactions can take place here? Well, nickel solid, if it reacts with lead nitrate, it's going to produce lead. So if nickel solid can react with lead nitrate, the products would be lead solid plus nickel nitrate. And the question is, which one of these two metals is more reactive? Nickels have higher activity, leads have lower activity. So this is good. This reaction can take place. So nickel can lose electrons. Nickel's going to nickel 2 plus. Nickel's losing electrons. Losing electrons is oxidation. So nickel can be oxidized by lead nitrate. But nickel nitrate, if we take the products here, can nickel nitrate react with lead? And if so, you'd be thinking the products would be nickel solid plus lead nitrate. Kind of the opposite of the reaction we just looked at. And the issue here is that leads have lower activity, nickels, of course, higher activity, so this reaction cannot take place. So nickel can be oxidized by lead nitrate, but nickel nitrate can neither react in a reduction or oxidation. It doesn't react at all. There'd be no reaction. So it can neither be oxidized or reduced for D. Okay, that's all for this activity. Thanks for the attention.